Welcome back, Honors Pre-Calc students. Today we are just quickly reviewing how to solve linear systems. So we've got three choices ahead of us. We want to make sure that you recall how to solve systems graphically, how to solve systems using substitution, and how to solve systems using elimination. So we'll start off with graphically, and graphically means that it's going to require us to create a graph. The trick with the graphical systems is that really your solution is only as good as your graph. So you've got to know how to graph whatever it is that you are presented. Here are two linear functions. And it also kind of probably requires a decent piece of graph paper or maybe a calculator or technology. So let's go ahead and try to graph these two linear functions. This one here is set up perfectly for graphing a line using the x and y intercepts. If x is 0, right, then y would have to be equal to 6. And if y were 0, then 2x would be equal to 6, or x would be equal to 3. And then I can go ahead and plot those points. And here, like I said, your graph, your solution's only going to be as good as your graph. So I'm going to go ahead and use a ruler. It's okay if you don't have one. If it was a quiz or test, I'd give you guys some graph paper. So there is my first line. And the second one, I'm going to run into trouble if I try to use the x and y intercepts, because here the x and y intercepts are one and the same, 0, 0. It's probably easier to rewrite this one in terms of y equals mx plus b, right? Solve it for y. I can see that this is one of my favorite graphs, y equals x, so 1, 1, 2, 2, and so on, 0, 0. I missed the best one. And we'll connect the dots. And I sort of got lucky because I just so happened to find that coordinate where they intersected. So this graph brings me to probably the most important point. What does it mean to solve any system? To solve a system means to find the point of intersection between the graphs. So here we just determined that the point of intersection was 2, 2. And I want to make sure that I indicate my solution as a coordinate. When you're solving graphically, again, you're kind of limited by how good your graph paper is. So I usually will either double check my work using one of the alternate methods listed below, and that's totally fine. If you're taking a quiz and it says to solve graphically, by all means, feel free to check your solution. But here, we'll just go ahead and check them by verifying that 2, 2 is indeed the solution for both of our equations. So when I plug in 2, 2, I would get 2 times 2 plus 2, which is indeed equal to 6. And on that bottom equation, I would get negative 2 plus 2, which absolutely is equal to 0. So it's always a good idea to check your answer when you're talking about graphical solutions, because it's very easy to maybe not read your graph correctly or be off by a little bit. So that is solving graphically. Can you graph the functions that are given and then determine their point of intersection? Our next option is to solve systems using substitution. And you would have talked about all these methods probably way back in Algebra 1, but substitution is essentially like renaming something. I like option 2 here. The example that I chose is perfectly lined up for substitution because the first equation is written so that one of the variables is already isolated. I typically choose substitution as a method when one of the equations is written in this form, because then it's really simple for me to go ahead and just notice that I can pop in that y instead of using y in the second equation. I'll pop in that rename, that 2x plus 2. So I'm going to use that first equation, and I'll rewrite the second equation as 4x plus. Instead of using y, I'll use 2x plus 2 since they're equivalent, and then I'll subtract my 5 and have it equal to 0. I always point out to students that you can see the architecture of that second equation, right? The only difference being that you've used the first equation instead of the y value. Now here I'm down to a one variable, right? One equation. So I can go ahead and solve this one out. I'd have 6x minus 3 by combining like terms, and that would solve out to be 3 over 6 or 1/2. Now, don't forget, your answer should be a coordinate like we just talked about. What we're really finding here is the coordinate where these two linear functions would intersect. So I'm going to go back to that first equation, and I'm going to use y equals, right? It's already set up to tell me the y value. So I'll go ahead and I'll plug in that solution, and I will add things together, right? I'll get 1 plus 2. I'll get y equal to 3. So my solution to this system is at 1/2 3. Last but not least, we've got the elimination method. Now notice here I don't have one of my equations solved for y equals, although the second one would be fairly easy to do. You could really quickly turn this third example into a substitution question. But I want to illustrate elimination. With elimination, your goal is to get rid of a variable by adding your equations together. And the key, though, is to get it so that one of your coefficients, the coefficients on one of your variables would be equal and opposite. So it's a little harder to make 2 and 5 equal and opposite, but if I took that second equation and I multiplied it by a +4, then I would have a 4 and a -4 in front of each of my y's. So I'm going to choose to multiply that second equation by 4. I'll recopy the first, just as it's written, still true. And I'll get 4 times 5, that's 20x plus 4y, and on the right-hand side, -4. And then I'm going to go ahead and I'm going to add my equations together. And what happens when I do that is I can combine my x's, I can combine my y's, but a -4 and a +4 makes a 0. So I'll be left with 22x on the left-hand side and a -11 on the right-hand side. Divide out, and again, I must have liked halves today. I got a -1/2 this time. If you're asking yourself, why in the world am I allowed to add equations? It goes back to the same kind of rule that tells us that we can multiply both sides by 4. If you have an equality, then as long as you do the same thing to both sides, it's perfectly allowable to do that to equations. So think of it this way. The top line is an equation. The bottom line is me adding, right, when I added those equations together, I'm adding the same thing on both sides. It's just that on the left-hand side, I have the expression, and on the right-hand side, I have the number. But they're equal because we were told at the beginning of the question that they're equal. So really, this line is me adding the same thing to both sides, just as I would if I was adding a 1 or a 2. And finally, we have to go back and we have to solve for our y value. You can return to either equation. I usually look for one that's easier to work with. Maybe everything's positive, so I won't make errors. Here, I kind of like the second one, because if I took that second equation, I could rewrite it as y equals -5x minus 1, and I'd have a direct route to y. I wouldn't have to divide at the end. So here, I'm going to get -5 times a -1/2 and minus 1. Or 5/2 minus, instead of writing it as 1, let's write it as 2/2. Or in the end, I get a 3/2. So my overall solution here is that those two linear functions would intersect at the coordinate -1/2, 3/2. Tomorrow in class, we're going to work through just examples with linear functions to make sure that you remember these methods. And then tomorrow night, your homework would be to watch the next video here in our little series, because in Honors Pre-Calc, we're going to work with nonlinear systems. What if you are solving with linear functions, with parabolas, or with circles, or with ellipses, or hyperbolas? Any of the functions, sine or cosine, exponentials, any of the functions that we've already covered in semester 1 are now fair game to be part of our systems. So we'll follow up with that tomorrow. Your only job tonight, though, was to review these notes and then come prepared to work on an activity together tomorrow in class. Thanks for watching.